Alright, so there are two different types of probability. There's theoretical probability and there's experimental probability. You need to know both of them. So for theoretical probability, whenever you see an uppercase italicized P like this, that means I'm asking you to find the probability of something. You're always going to see it next to a set of parentheses, and there's going to be something inside the parentheses. Okay, so I'm going to talk about this and do an example at the same time. So if I'm thinking about a die, and I put an italicized P and I put a 2 in there, what this is saying is find the probability of rolling a 2. Okay, so what's the probability of rolling a 2? Well, we write that by reading these right here. Your numerator is your number of favorable outcomes, which means how many 2s are on a dice? 1. Your denominator is the total number of possible outcomes. So how many outcomes are on a die? 6. Therefore, the theoretical probability of rolling a 2 on a die is 1/6. What's the theoretical probability of rolling a 3?
1/6.
What's the theoretical probability of rolling a 4?
1/6.
What's the theoretical probability of rolling odd?
1/2.
1/2. 3/6 or 1/2. Okay, those are all in theory. That's what's supposed to happen. Is that always going to happen? No. If I roll a dice 6 times, am I only going to get a 1 2? Or is it possible that I can get 0 or 3 or 2 2s?
You can't get 0.
It's possible to get any of those. If I roll a dice 6 times, it is for sure possible that I might not get any 2s. When you actually do the experiment, when you actually roll the dice, okay, or the die, that's called your experimental probability. Okay, so it'd be written the same way, and I'll ask you whether I want experimental or theoretical. So you'll still see the uppercase italicized P, and then the event, whatever it is that I'm asking for. And the way you write this one is the number of times that event occurs. So if I ask you for an experimental probability of rolling a 2, you would write that as, let's say we did it 20 times. And let's say I rolled a 2 3 of those times. My experimental probability would be 3/20, which then you can change into a decimal and a percent if I ask you to. So an experimental probability is what happens when you actually do it. If you want to put actual underneath here, you can, but it's what actually happens. So you have to perform the experiment in order to get that probability. Okay? Sometimes I can give you a picture of an experience. So maybe I give you 20 dice and they all have a different number on top of them. And I can ask you, what was the experimental probability of this situation? So you don't always actually have to roll the dice. I can give you a picture of what happened. And then we'll talk about what that means in a second. Questions on these two? So let's go ahead and do some of these. Take a second and I want you to draw. I know it's kind of hard to see. I took it out of a book. Draw this spinner. So make a big circle and I want you to split it into 10 even pieces as evenly as you possibly can. So I would split it down the middle once, and then you're going to have to split each side into 5 pieces. There's really no other easy way to do it. So go ahead and draw that spinner for me because we're going to answer questions about it. So let's go ahead and start doing some of these together. So it says, suppose you spin the spinner once. Find each probability. So I want the theoretical probability here. So for number 8, it says, what's the probability of rolling or spinning a 12? Well, to write this, we need to figure out how many 12s are on here. None. 0. So 0 out of 10 possibilities gives us a probability of what? 0. It's never going to happen. 9. What's the probability of rolling a 2 or a 4? Well, we have a 2, we have 1 4, so how many possible choices do we have? 2, right? We have 1 2 and 1 4, so we have 2 of those over how many choices altogether? 10. We have to simplify. So this equals 1/5. What's the probability of spinning a multiple of 3? So we need to come over here and we need to find all of our multiples of 3. Well, 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. Are there any more?
No.
No. So our multiples of 3 are 3, 6, and 9. So how many multiples of 3 are there?
3, 10.
3. And how many possible choices are there?
10.
So 3/10. Let's do one more together and I'll see if you guys can do the last few on your own. So the probability of spinning an even number. Well, we need to go through and we need to find all of our even numbers. So we have 2, 4, 6, 8, 10. How many even numbers are on that spinner?
5.
5 out of how many numbers altogether?
10.
Which equals
1/2.
1/2. Oh, I'm doing it the wrong one, huh? This one? There we go. All right, you guys go ahead and take 2 minutes and finish 12 through 15. Go ahead and check your answers for 20 through 23. So for 20, the probability not green, so that means everything else, is 3/4. And then 21, the probability of purple or blue, well that's kind of the same thing because it's 3/4. The probability of white is 0. And then the probability of not purple, so blue or green, would be 2/4, which you can simplify to 1/2. So let's move on to a spinner activity. This is what I was excited to show you guys. Oh, I gotta figure it out first. There we go. So here's a spinner. And we're going to go through and talk about what the theoretical probability is up here. And you don't have to write this down. We're just going to do this together. And compared to the experimental probability. Okay? So theoretical probability of spinning a 7. There's 1 7. So we have 1 out of how many? 8. So theoretically, 1 out of 8 times, I should spin a 7. Now, is that going to happen? Well, we'll see. Let's do it. I'm going to set up a frequency table over here. So I'm going to start at 1, 2, 3, 4, 5, 6, 7, 8. I'm going to put my tallies in the middle and my frequency over here. And let's go ahead and do, how about 24 times? Because the reason I picked 24 is because I should be able to simplify at the end to 1/8. So we'll see if that actually happens. So I gotta remember how to spin this. It actually makes noise too. Oh, that's gonna take forever. So we got a 3.
What?
What do you mean? It's right here, 3.
Oh.
Okay. Oh, this is gonna take forever. Oh, see? You gotta think that's cool. Oh, we got 3 again.
Are you just stopping them on 3?
I'm not stopping anything. It goes on its own. 4.
So close.
With our over here, I'm gonna go ahead and write the frequencies. So we have 3, 4, 6, 2, 1, 1, 3, and 4. Okay? So now we can take these frequencies, and if we add them together, we better get 24, because otherwise I'm going to blame you guys, because you're the ones that counted. So we're going to go ahead now. So we're going to take the 3 that we got for 7 and put that in our numerator when we go through and simplify. Believe it or not, we actually get 1/8. So in this case, our experimental probability and our theoretical probability are the same. Now that would only work with if I chose the probability of 1 or 7, because those are the only ones that I spinned that number 3 times. I have another one for you guys. It's with dice. So we're going to do it a little bit differently for this one. I'm going to change it to 1 die though. So if I have 1 die, what is the theoretical probability of rolling an even number? William?
1/2.
1/2. So it's 3/6 or 1/2. And yes, I can change the color.
Blue. Green. White. Blue. No, yeah.
Alright, blue it is. So what I'm going to go through, and I'm not going to do as many for this one, let's do 10. So for my experimental probability, I'm going to do 10 rolls. And my options are 1, 2, 3, 4, 5, or 6. And so since I'm talking about even numbers, I'm going to go ahead and highlight these just so we can see them. And let's go ahead and roll this 10 times. I think I click here. I just have to click on it. So there's 1. And a 1. And a 4. Alright, so so here is our experimental probability. I have only 2 evens out of all of those rolls. And when I simplify this, I get 1/5. So our experimental probability of rolling even turned out to be 1/5. It's not the same as our theoretical probability, but that's okay. That's why it's an experiment. It doesn't have to be the same. It should be pretty close, but in this case, we're quite a bit off on this one.